Ever wonder how AI systems decide when to use a calculator, a search engine, or a code interpreter? It's like teaching a robot to play chess. Sure, you can show them the pieces, but how do you help them understand when to move a knight or a queen? Today, we're diving into a breakthrough that's making AI smarter about tool use, and it all starts with something called first-order logic, or FOL, as the cool kids call it. Here's the problem. Large language models, LLMs, are incredible at pattern recognition, but they're not natural problem solvers. They need structured guidance to know when to pull out a tool. Traditional methods rely on the AI generating its own training data, like asking a kid to write their own math textbook. Spoiler, it's messy. Errors compound, and the model ends up guessing instead of reasoning. But here's the twist. Researchers are now using knowledge graphs, digital web-like structures mapping relationships between concepts, to create clean, precise training data. Imagine a graph where climate change right arrow causes extreme weather, or Albert Einstein right arrow studied right arrow physics. Every node is a concept, every edge a relationship. It's the ultimate cheat sheet for AI, but with a twist. It's not just data, it's structured logic. Now here's where FOL shines. Think of first-order logic as a formal language that turns these relationships into precise, executable questions. For example, if the graph says, solar panels right arrow reduce right arrow energy costs, FOL might translate that into, what is the effect of solar panels on energy expenses? It's like giving the AI a recipe for reasoning, step by step, no guesswork. Here's the magic. The researchers used FOL to create query pathways through the knowledge graph. Let's say the graph has a path from renewable energy, right arrow, solar panels, right arrow, cost savings. The AI doesn't just see those nodes, it learns to ask, how do solar panels lower energy bills, and then follow the steps. 1. Fetch efficiency data. 2. Use a calculator tool. 3. Present the results. It's like teaching a robot to solve a puzzle by showing them the pieces. And the results? When tested, even a small amount of FOL-powered data made LLMs way better at tool use. It's faster, cheaper, and more reliable than old-school trial and error. No more sifting through AI-generated garbage, just clean, logical steps. So why does this matter? Picture an AI that can diagnose a medical condition by cross-referencing research, calculating treatment costs, and generating a patient-friendly summary. That's not sci-fi, it's the future of AI. Let's break it down with a simple puzzle. Imagine you're told, find the value of A where this condition is true. In logic terms, that's written like Q equals A, pred 1, AA. Think of it as a search. What is a such that the predicate pred 1 applies to A? Let's make it real. If pred 1 is get the profession of a person and A is Fred Willard, the answer is straightforward, his profession is actor. But here's the twist, what if there are multiple conditions? Like find the person who is both a chef and a musician in Paris. Suddenly, the logic gets trickier. The system has to juggle overlapping rules, cross-check data, and resolve conflicts. This is where the real magic happens. Researchers test these patterns by building virtual worlds with rules and asking tricky questions. They track how systems like AI or search engines navigate these puzzles. The goal? To make technology smarter at handling real-world complexity, where answers aren't always black and white. Next time you ask a smart speaker a complicated question, remember, it's wrestling with the same kinds of logical puzzles we're talking about here. And the better we understand these patterns, the closer we get to machines that truly understand us. Want to see how this plays out in real experiments? Stay tuned.